Here I'd like to look at a specific class of series that has a lot of really nice properties and also tends to come up a lot in applications. And a geometric series is a series of the form a plus ar plus ar squared plus ar cubed and so on. And the key characteristic about a geometric series is that you notice that there is some common factor r that can be used to generate the terms of the series. In other words, I'm starting with some first term a1 here, and then I'm multiplying that by some factor r to get the next term. And then I multiply that by the same factor r to get the next term, right? So we see that there's this common factor r that gets multiplied to go from one term to the next, right? So r is called our common ratio. And you can think of it as the ratio of two consecutive terms of the series. In other words, if I take any term, say, one random term here, I can divide the previous term and that would give me r. So take I can divide by the previous term ai minus 1, and that will give me the common ratio r. So if I see a series that has this particular property, then we know it's a geometric series. And one thing that's particularly nice about a geometric series is that it has a very simple and easy to compute sum. And let's think about how we would go about forming the partial sum formula. We know that, for instance, here if I were to write out Sn, I would be just summing up a plus ar squared and so on out to the nth term, which would be ar to the n minus 1. Now if I multiply this by if I multiply both sides of this equation by r, so r times Sn, then I get ar plus ar squared plus ar cubed, so on, all the way out to ar to the n. And then if I subtract the two equations, notice here on the left-hand side, if I do Sn minus r Sn on the right-hand side, well, I notice a bunch of terms would cancel. Right, so I would have a, and then ar minus ar, those would cancel, ar squared minus ar squared, ar cubed minus ar cubed, all those terms are going to cancel, right? And then I'd have ar to the n minus 1 minus ar to the n minus 1. But then I would have also minus ar to the n. It doesn't cancel. So basically all the stuff in between here is canceled when I subtract. But what remains is a minus ar to the n. Now, if I were to try and isolate Sn in the equation, then I get my formula for Sn. So here I'll factor it out. So if Sn times 1 minus r equals a times 1 minus r to the n, and then dividing by 1 minus r, I get my formula for the nth partial sum of a geometric series. So the nth partial sum would just be our first term a times 1 minus r to the n over 1 minus r. That would give us the sum of, that would be a formula that gives us the sum of the first n terms of the geometric series. So here's our partial sum formula. What happens as n goes to infinity now? Can we take the limit as n goes to infinity to find the sum of the series? So we can ask this question, what happens as n goes to infinity? And one thing we can remember here is if I'm taking the limit as n goes to infinity of, say, r to the n, we've seen this before, there are several possible outcomes here. For instance, we noticed that if if r is less than 1 in absolute value, right, we saw this, then we know this limit will be 0. If r is equal to 1, then we know this limit will equal to 1. And if r is greater than 1, or r is less than -1, then we know that this limit will not exist. It'll be either infinity or some value that doesn't exist. So between these three cases, which one is going to be the one where we get a convergent series? So we know that when I take now the limit as n goes to infinity of Sn, in other words here, the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r, well, we can look at how this part of the series behaves. As n goes to infinity, if r is less than 1 in absolute value, then this will equal to 0, right? Or this r to the n here will go to 0. So we see that if r is less than 1 in absolute value, then this series becomes as a sum of a over 1 minus r. Now this is only in the case if the absolute value of r is less than 1. So the question is, what about the other cases? If the absolute value of r is greater than 1, we'll notice then here the series would be divergent, since the limit as n goes to infinity of r to the n doesn't exist. So if r is greater than 1 in absolute value, then the limit as n goes to infinity of Sn does not exist. And then the other case, if r is equal to 1, what can we say then? Well, in this case, we can think about the series written this way. Notice that this would just be, if r is equal to 1, then this series would just be adding up a plus a plus a infinitely many times. So its partial sum would just be n times a. And so taking n to infinity, this would go to infinity. So this is divergent in that case as well. Okay, so we see that the case when we know that this geometric series will converge will be this case here when the absolute value of r is less than 1, in which case this will tell us that this a over 1 minus r will give us the sum of the series. On the other hand, if the absolute value of r is greater than or equal to 1, then we see that the series will be divergent. Okay, so that's what we see here. The geometric series is convergent if the absolute value of r is less than 1 and its sum is given by a over 1 minus r. If the absolute value of r is greater than or equal to 1, then the geometric series is divergent. Okay, so it'll be convergent if the absolute value of the common ratio is less than 1, in which case we have the sum formula here. Alright, so let's practice this a little bit. Suppose I have this geometric series 5 minus 10 over 3 plus 20 over 9 plus 40 over 27 and so on. So let's first verify that this is geometric. In other words, is there some common ratio that I can use to generate the terms of the series? So what I notice here is that to go from 5 to negative 10 over 3, I have to multiply by negative 2 over 3. Right? Because 5 times negative 2 over 3 will give me negative 10 over 3. And here to go from negative 10 over 3 to 20 over 9, again, I'm multiplying by negative 2 over 3. And then to go from 20 over 9 to negative 40 over 27, there again, I'm multiplying by negative 2 over 3. So that shows us that, first of all, this is a geometric series with a common ratio r equal to -2/3. Okay, and since here the absolute value of r would be +2/3, and that's less than 1, that means that the series is convergent. Moreover, we know exactly what the sum of the series will be. It's a over 1 minus r, and a was the first term of the series, in this case 5. And r was -2/3, so we have 1 minus -2/3. So it'll be 5 over 1 plus 2/3, which is 5/3. And simplifying that, I think we just get a sum of 3. Okay, so we see here, we first verified it's geometric, figured out what the common ratio r is, showed that because the absolute value of r is less than 1, it's convergent, and hence then we can find the sum of this series using a over 1 minus r. Let's try it with an example like this. Notice that the way it's written here is a little different. But let's first of all verify that this is a geometric series. If I were to write this, you got 2 to the 2n times 3 to the 1 minus n. What I could do is, if I bring 3 to the 1 minus n to the denominator, I can make it a negative power. And so if I bring it to the bottom with a negative power, it becomes 3 to the n minus 1. Now let's look at this as 2 to the 2n as 4 to the n. 3 to the n minus 1, I can look at that as 3 to the n times 3 to the -1. So in fact what we see here is that the series is the same as 4/3 to the n times 3 to the -1 here in the bottom would be 3 to the +1 in the top. And notice here that this is geometric, right? Because here we've got each subsequent term of the series gets multiplied by 4/3. If you're not sure about that, what you can always do is you can write out the terms of the series. Here, let's write out what the first few terms would be. So I think when n equals 1, we get 4/3 times 3 is 4. When n equals 2, I have 4/3 squared, which is 16/9, times 3, which would be 16/3. When n equals 3, then I get 4/3 to the power of 3, which is 64/27, times 3, which is 64/9. Okay, and so on. So you can see that each subsequent term of the series is generated by multiplying the previous term by 4/3. And that was kind of what we observed here with just these first few terms that we wrote out. And that's exactly what we have here. So this series is written in the form where we can see here, this is your r, 4/3, the thing that's being raised to the power of n. So since the absolute value of r here is still 4/3, and that's greater than 1, that implies that the series is divergent. Since it's divergent, there is no sum. In other words, what we notice is that the terms of the series are going to keep getting bigger and bigger. And so the series will not converge to a finite value.